Welcome back. In the last class, we started discussion about two-dimensional NMR, where I briefed about the need for a two-dimensional NMR and the limitations that are present in the 1D NMR. And I explained what happens if I have a complex molecule with a complex spectra, why 1D is difficult to analyze. I don't say it's impossible. It's difficult to analyze what is the resolution problem you are going to get, and simultaneous detection of two nuclei and forbidden transition like multiple quantum etc. cannot be detected. So with several limitations were there. Then I showed what is the need to do a two-dimensional NMR. So this is the reason why we have to start using 2D NMR. So this is a general pulse sequence. In fact, last class I showed you a 1D NMR is one. You apply one radio frequency pulse, bring the magnetization to XY plane, start collecting the time domain signal, do the Fourier transformation. Single time domain data, single Fourier transformation gives you single frequency domain spectrum. This is the one-dimensional NMR. In the 1D NMR, you get the chemical shift information on the x-axis and the intensity on the y-axis. Of course, we are not very much worried about the intensity at the moment. We are worried about only time period to discuss the dimensionality. So, one-dimensional NMR is simply, remember, it is because of one time period and you do single Fourier transformation, you get a single frequency domain spectrum. Now, coming back to the two-dimensional NMR, it is a general pulse sequence I have written. Any two-dimensional NMR, for that matter, any two-dimensional NMR consists of basically 4 time periods like this. It has 4 time periods. So, what is happening here? Look at it. This 4 time period has been divided into preparation period, evolution period, mixing period, and detection period. This is a mistake. It is a detection period. Okay. Okay. So this is a detection period. These are the 4 periods that any two-dimensional pulse sequence will have. What is happening in each of the pulse sequence? Each of the pulse blocks. First, in the preparation period, what happens is we allow the spins to relax and attain thermal equilibrium. So we prepare the spin system for doing a specific experiment. We allow the spins to relax here and attain thermal equilibrium, do whatever you want for the next pulse to be applied, and what information you want to do get this in this pulse sequence. So correspondingly, so we will prepare the spin system here. Basically, in most of the cases, the preparation period is for allowing the spins to relax and attain thermal equilibrium. Of course, P1 and P2 are the pulses we apply for this and this. Let us not worry about it. We will discuss only the time periods. After the preparation period, you apply a radio frequency pulse and bring the magnetization to XY plane. Here, the spin starts evolving. Evolution takes place. Like we talk about human life evolution, the magnetization starts evolving and evolves depending upon the information content is already present here. For example, it can evolve due to chemical shift, it can evolve due to relaxation. So various information content is there and it starts evolving here. And what we try to do here is this time period is additional compared to normal one-dimensional experiment. One-dimensional experiment is only this part. We have a pulse here and collect the signal and do the Fourier transformation. But if we have extra period here, this period is not constant. Unlike detection period, which is constant, this evolution period is not constant. This additional period is systematically varied such that spins are allowed to evolve as a function of T1 period. So this is the important point. Remember, this is not a constant period. And next period is what is called mixing period. This period is optional. The third period is mixing period. We can have it or we need not have it. It is our choice depending upon the type of experiment, type of pulse sequence we are designing. In this case, if at all it is present also, what happens is the information from one spin is relayed to other also in this case. Of course, same thing happens here also, but here this is another thing where mixing period, information one spin is relayed to other here. That is the role of the mixing period. The last is the detection period. Before that, of course, we apply a detection pulse of varied angle. For example, in the case of depth experiment, which I said, we have a different flip angles like that. So we can have different pulse sequences. It can be a 90-degree pulse, 45-degree pulse, whatever it is. Finally, it's a detection pulse we apply and start collecting the free induction decay. And signal is collected as a function of time, and we do the Fourier transformation here. And this detection period is a constant duration. T2 is constant. We are not varying T2. Only we are varying T1. You understand? There are two time periods. One is a constant period. Other is a variable period, which is constantly varied. Okay? Systematically. How we acquire data? For example, when I said T1 is systematically varied, how do I vary the T1 here? How do we acquire data? And diagrammatically it is shown here. Now we have a preparation. This is the evolution, mixing, and collection of the FID. We start acquiring FID. How we increment T1? Initially, let us say there is no delay. T1 is 0. Absolutely no delay at all. I'm sorry. Now we give a small time period here. T1 is put, and here FID is collected. Signal is collected here. Now, as a consequence, the delay, it's this. There was no delay. Now the gap increased. Now we add some more delay. Increment the delay. Like initially, let us say 5 microsecond. Next we have 7 microsecond, 8 microsecond, like that. What is happening? Every time I am increasing the time delay T1. But notice one thing. This is constant. I am not incrementing this. Only this period is incremented. You keep on incrementing like this. Now we completely acquired the signal in 2 dimension. In T1 dimension also we acquired signal. This is the T1 dimension. This is the T2 dimension where we have a data acquired, which is the constant period of time. So systematically we vary T1 period, collected signal here, and also collected here. This is basically what we do generally in most of the 2D sequences. Okay. If you see pictorially, it is like this. Look, initially there was a small time period in the evolution which keeps on getting incremented. Small increase, small increase, small increase, small increase. That's what I showed. Finally, we have whatever the time period we wanted, so it keeps on increasing. And we have a mixing pulse, so we add afterwards mixing time, afterwards read out pulse and start collecting the FID. See here, this is getting changed, but here it is always constant. T2 is a constant. In this particular example, we have our readout pulse means a 90-degree pulse. That itself we can consider as a mixing pulse and also detection pulse. Now, no problem. But here mixing pulse is absent. We will apply only a 90-degree pulse and collect the signal. This is similar to the pulse sequence what we see in the coming slides today called a COSI. It is similar to COSI experiment. You understand? This is pictorial how we can see the 2-dimensional time domain data. So how many time domain data we have here? One is the time domain data here, other is the time domain data here. I said time and frequency are Fourier pairs. We have to convert them to frequency domain. We will do that. So now 1-dimensional signal in T2 dimension is they collected after each T1 increment, like see, like this. What happens? I keep incrementing the T1, FID is like this, and do the Fourier transformation. In the F2 period, the signal appears with a different phases like this. Why? Because when there is a delay in the sending the pulse and start collecting the data, there is always a phase delay. So there is a phase distortion will be there. But this case, phase is uniformly changing because we are uniformly changing this. Look at this one. This is a signal intensity. It's positive like this, phase goes like this, and finally it goes. So you can have typically 100 to 125 to 520 points or even 1K data points depending upon your size of memory and the information content you want. Depending upon what type of information you want, you can have that many number of T1 incremental points. That's fine. Now, look at this one, how we visualize a FID in the T1 dimension. So far, remember in this case, I was showing only T2 domain FID, which changes phase as we keep on incrementing the T1. Every time we collect this signal, you just let us say I collected this signal, you get this FID, this spectrum. Yeah, I collected this FID after 150 microsecond. This is spectrum. No phase correction is done. Simply we collect the FID and do Fourier transformation. This is what we have got. Okay. So now what we can do is each T1, if you collect signal and do Fourier transformation, you get a spectrum. Let us do one thing. We collect only one of the signal. Let us say in this case, you have collected one signal like this, any one of them. See how it is varying. If you collect only one of them, follow the intensity pattern as a function of T1. This being constant here. Now what is happening? It keeps on going like this. Look at it. It traces the top of the peak here. It keeps going like this, comes down, goes negative, 0, goes. What is happening here? If you look at it very carefully, this is an oscillatory function. Look at it. It is like a regular free induction decay. What to collect is oscillatory function. Is it not? Exactly. In the T1 dimension, indirectly, you have created a free induction decay, a time domain decaying, oscillatory and decaying signal you have created. In the time domain, that's precisely what you are going to have. You are having a FID, free induction decay in the T1 domain, and also you have FID in the T2 domain. That's how you indirectly created. So in this, finally, actually, if you have many such frequencies, in the T1 dimension, you also have an interferogram, exactly like this. I took an example for only single frequency, how it is varying to show it is an oscillatory function, and also it is a decaying function like this. It is decaying FID. Damped oscillations are there for one frequency. If you have n number of frequencies, n number of peaks present, you have an interferogram like this. And that is what happens in the 2D data acquisition. You create an FID indirectly in the indirect dimension by systematically varying the T1 time period and correct the FID in the T2 period for a constant time. This is what is happening. Now, simple logic you extend. In this one-dimensional NMR, we had a single time domain data. We did single Fourier transform and get a single frequency domain spectrum. That's all. One time domain data, one Fourier transformation, you get single frequency. Now we have a two-time domain data. Data acquired in the time domain, oscillatory decaying, damped oscillation decaying signal in the T2 period and also in the T1 period. So we have two time domain data, make double Fourier transformation in both the dimensions. Do the Fourier transformation in this dimension and Fourier transformation in this dimension. Or in other words, do the Fourier transformation in the T1 dimension and also do the Fourier transformation in the T2 dimension. You can do double Fourier transformation. What you are going to get is two frequency domain spectra. So you are going to get frequency in both the dimension. Let us see how we can see the spectrum from the time domain data. This is, I showed you, we keep on incrementing and finally acquired the data, right? This is the time domain data acquired by incrementing systematically the T1 time period. I increment the time during T1 and collected the FID. Now what we do is, we can individually do the Fourier transformation, convert time domain data of T2 domain or T1 domain to frequency. First, let us say we are doing the Fourier transformation in this dimension, in the T2 dimension. So this is remaining same. Let us say we have 4 frequencies present here. In the T2 dimension, we have 4 peaks. But in the T1 dimension, it is still a data point like this. It is a time domain signal. It is varying signal. Okay. Now we do the Fourier transformation. Also simultaneously or immediately after this, we do the Fourier transformation in the T1 dimension also. Now we are going to see only frequencies. In this dimensions also you get frequency. In this dimension also you get frequency. Now if I look at this peak here, I can say in this dimension, in the F2 dimension or T2 dimension, see dimension can be mentioned in T2, T1, F1, F2, omega 1, omega 2, direct dimension, indirect dimension. These are the nomenclatures people use. For example, T2 dimension, it is a direct dimension where we detect the signal. After Fourier transformation, it is a omega 2 frequency. Or this is called F1 and F2 are the two frequency dimensions. It is called F2 dimension. Similarly, this is called F1 dimension, T1 dimension, or omega 1 dimension. Since it is a direct dimension, we detect the signal, it is called direct dimension. This is indirectly we are acquiring signal, it is called indirect dimension. These are the nomenclatures which are adapted and it is you most often come across in the textbooks and literature. Please don't get confused. Everything is same. It's only the way we use it. So now you read the spectrum. If I come here, just exactly look at this in the omega 2 dimension, I have a frequency here. And the same peak, you go in this direction, in the omega 1 dimension, this is frequency. So that means this peak has a particular frequency here in the omega 1 dimension, and it has peak frequency here in the omega 2 dimension. This frequency can be said we have two frequencies. One in this direction is one frequency, in this dimension you have another frequency. So we can now, looking at the where the peak is coming, I can say what is its frequency here and here. This is the way you can represent the two-dimensional data after Fourier transformation. So we got frequency in both the dimensions. Excuse me. Now we'll generalize dimensions, higher dimensions in NMR. First, this is the basic thing I said. 90-degree pulse, collect the signal as a function of time. One time domain and one frequency domain. It is a one-dimensional data. It is called one dimension. Now we have two time periods. I can do double Fourier transformation and I get two dimensions. It is a two-dimensional sequence and we get two-dimensional data. There is no reason why we have to stop here. Depending upon relaxation time, how long the free intention peak will last, we can design more number of experiments. More time dimensions we can add. For example, I can have a 3 time periods like this: T1 period, T2 period, and T3 period. This is 3 dimensions, 3-dimensional Fourier transformation I get, and then 3-dimensional spectrum I am going to get. See, 2-dimension is like this, 3-dimension is, you can imagine a cube, a box. It is like a box. You can have one dimension here, and one dimension here. So 3 dimensions are there. We can have 3-dimensional spectrum with the 3 time periods. So this is how we get. Now the question is, with this we can generalize and say, what is that which defines the dimensionality of a number? Simple logic. A pulse sequence containing n time periods gives n-dimensional spectra. Remember, you can have a pulse sequence containing n time periods, like T1, T2, T3 are the nomenclatures we use, and gives n-dimensional spectra. So we have 2D, 3D, 4D, etc. spectra. Important point to remember, in n time periods, n-1 periods are varied. Remember, in the 2-dimensional data, T1 was varied. T2 was kept constant. Okay, I showed you the example. T1 systematically it was varied, but the T2 period was kept constant. Similarly, in n time periods, n-1 periods are varied, and the duration of the last period, that is called a detection period, is always constant. Always last detection period is kept constant. And each time period, we have to increment the data to create a pseudo FID. Exactly what we did in the 2D I showed you. The free induction decay was created by systematically incrementing the T1 points. That is pseudo FID. So we created a pseudo FID in time domain, and the T2 domain detection period, we have a regular FID. Same way, if you have n-dimensional n-time periods, you have n-dimensional spectra, and we can have n minus 1 pseudo FID is created, and last one is the real FID we collect in the detection period. Of course, this is a general sequence. Of course, you can keep some of the periods constant depending upon what type of experiment you want to do. All those things, there are various possibilities you can think of. Maybe in after in that, maybe one of them deliberately you can keep constant for getting some information. All play you can play around. But general say is in the n-dimensional data, n minus 1 periods are systematically varied. Now, this is the logic. Pulse sequence with n time periods gives n time dimensional data. You do n dimensional Fourier transform, you get n dimensional frequency spectrum. This is called n dimensional NMR. You understand? Pulse sequence with n time periods gives n dimensional time domain data. To the n dimensional Fourier transform, you get n dimensional frequency spectrum. It is called ND NMR. Now we can see how the spectrum looks in the two-dimensional way. We can have a spectrum like this. Okay, this is the frequency domain in here, and also here a frequency domain. This is a resolve type experiment where chemical shift information is here, J coupling information is here. They are all resolved. They are separated. This is a correlated spectrum where frequency of one nucleus is correlated to the frequency of the other nuclei here, or frequency of the same nuclei between two different nuclear spins can be correlated. It could be chemical shift of one nuclei here, chemical shift of other coupled nuclei here. That's also possible. So these are all, I gave you two examples. This is the way we represent the two-dimensional spectra. This is called stack plot. When you plot like this as a with an intensity pattern like this, and one page as a function of this number of stacks depend upon number of T1 points you had. You can represent like this. This is a stack plot of the 2D spectrum. Understand? It's a stack plot of the 2D spectrum. You can define the number of T1 points or incremental points and have a stack plot of the 2D or 3D spectra. But remember, this is okay for 2D. You can have a stack plot. How do you want to have a 3D? Very difficult to see and imagine. Okay? As a consequence, it has been modified. The stack plot like this, it can be modified to give a spectrum like this. This is a stack plot. This is called contour plot. See each peak here. For example, 1, 2, 3, 4 peaks are there. They are represented as contours here. And each here in 2D spectrum, this is a spectrum like this, exactly similar to this. But what you got the vertical peaks with some line width, what you saw in the 1D spectrum, one-dimensional spectrum, same thing has been converted into a sort of contour, like concentric, like circles, one within the other. Several circles are there. Okay. So these are all called contours. We have different contours, one within the other. There are several such contours, maybe 1, 2, 10, 20. Number of contours will be there. Mind you, area of this contour exactly matches with the area of the corresponding peak in the stack plot. For example, I consider this peak, which is highly intense. Okay, and the area of that peak and this peak perfectly agrees. Okay, this is a just translation of the stack plot. The peak, which is in the normal one-dimensional pattern, will be transferred to a contour like this, so that easy representation. This way we can represent much easily. So in all ways, this is the way which is represented. This is called a direct dimension, that the detection dimension, F2, omega 2, etc. This is F1, omega 1, indirect dimension. etc. Okay, this is the way we represent 2D data, but this type of stack plot is outdated. Nobody will do it. You always require only contour plot. Remember, all the time we use only contour plot for representation of any 2D spectrum, 3D spectrum or 4D spectrum. Doesn't matter. Any multi-dimensional spectrum nowadays are represented only by contour plots. Now, you may ask me a question, how did this peak stack plot was converted to a contour? How do I translate this peak into the circles like contours? I'm trying to give this picture for you. Look at it very carefully. This is imagine it's a mountain, a steep mountain. Now what you can do, you start from here, go around. I cannot go, you have to go behind this. Okay, I cannot I cannot go behind this drawing. But imagine you are going around there's a hill like this. You from the bottom, go around the hill like this. Find the area. Okay, and then what you do is, this is the area of this mountain at this point, at the bottom, and then put a circle here corresponding to this area. This is the area of the circle, which is the area you got by going around this mountain in a circular manner like this. Now I go slightly above, again go around the mountain, find out the area or circumference, come back and put it here. Now again go up, measure the area, come back and put another one like this. Keep on going above and above the hill, go around the circumference, measure the area, come and put here. So it is like area of circles at different places. You understand? Now this is a circular, I am going to a circular path here. When I go to a circular path here, this is area of a circular path here, here. And each time what you are going to get is translated into the contour like this. This is how the stack plots have been converted or translated into the contours. Now this representation is much easier, is it not? Compared to this. This is very clumsy. One peak is fine. If you have 100 peaks or 1000 peaks, you cannot have like this. It is very clumsy to see. That's why these stack plots are nowadays represented as a contour. This is the way you undergo translation of that. Area of the contour, if I said, now we have done one thing. The area of the entire peak here, as I said, with an example of different mountain, at different places is taken and represented here. So what it means, the area of this entire peak correspond to area of this contour. That's all. The integral area of the contour is nothing but the integral area of this stack plot. This is what I wanted to show you. Now, there are many examples. We go ahead and see multiple multi-dimensional spectra. Just to give you how we represent contour plot of different multi-dimensional NMR spectra. This is the 1D, this is 2D, and this is 3D. The one-dimensional spectrum, we have a frequency domain here, frequency in this axis that are chemical shift, and only peaks here. Here, in the 2-dimension, you can have one frequency domain here and frequency domain here. It's 3 dimensions, one here, and one in this direction. And this is something is written here. The molecular weight is up to 300. The 1D is very easy to handle, up to molecular weight of 500. Very easily will get it. Let us say I go to molecular weight of 10,000. Still not bad. You can manage with 2D. You see, still you get well resolved peaks. Peaks are very well resolved here compared to this and this. Okay. Imagine in this region if there was a stack plot, how clumsy it would have been. So that's why very easily we can represent this in the way, and we can see this type of thing. We can still get better resolution up to molecular weight of 10,000. You can still manage 10,000 Dalton. We can work with 2D spectra. Still, that is enough to give you the information. You can get complete information from 2D. But when it exceeds that, go to that as a molecular weight 30,000 or even more. 2D is not sufficient. Then we need to go to higher dimensions to get better resolution, to resolve the information in different direction, to coordinate the information in different direction, so that analysis become more simpler. So if molecular weight is even higher, we will see, we may have to go to even higher dimension. This is how it is. The dimensionality of the spectrum way do you represent the contour plot is like this. 1D is simple. It is a peak height, frequency, and the peak here. 2D and 3D and onwards, 2D onwards, everything will be in the contour fashion. Okay. And molecular size also defines type of experiment you want 2D or 3D. Now, what is the time constraint? There is a time constraint. You cannot just like that start doing the higher dimension experiment. Remember, if I take a 1D experiment, I nowadays with the present day sophisticated spectrometers, thanks to many vendors who have developed and designed very sophisticated experiments, probes, and then NMR spectrometers, magnets. Nowadays, compared to about 2 to 3 decades back, the time which is required to get a NMR spectrum is really fast. It doesn't take much time, very less time. In fact, 1D NMR you can do in fraction of a minute now. In about less than a minute, you can get a spectrum because sensitivity is much better compared to olden days in the present day spectrometer. 2D you can do it in few minutes. Let's say in 15, 20 minutes or 30 minutes, you can get a very good quality 2D spectrum. The same molecule, if you want to do 3D, it will take hours. Now I have this molecule, let us say, is very big. I want to do 4D, it takes days. If I want to do 5D experiment on that molecule, it takes weeks. Remember, weeks of the instrument time. And measurement time exponentially increases with the increasing dimensionality. So we have to be very choosy and finding out what type of 2D experiment or 3D experiment or 1D you require for your sample. So because measurement time goes exponentially with increasing dimensionality, look at here, it is almost exponentially going like this. Okay. And also it depends upon the molecular. For example, look at it. In the 2D NMR, up to 20 kilodalton is manageable, 0 to 20. 3D, it's okay, 20 to 30 is still okay, 30. Above that, you need 4D NMR. And even bigger molecule, you need in 4D NMR plus additional NMR techniques called TROSI, etc., which you do not know. I don't know whether I will have time to talk about TROSI. These are really sophisticated things which I don't think for your routine analysis you require in this. I don't think I have time to cover in this course. But basically, you remember, depending upon the molecular weight, you have to choose the dimensionality. And okay, this and increased information and resolution will be there with increased dimension. From here to here, if I come, I get better information, better resolution. Here to here, even better information and better resolution. Like that. Dimensionality has to be chosen based on the size of the molecule, based on the molecular weight. As you go from one dimension to a next higher dimension, you have more information and more resolution. But of course, you pay a penalty. You take more time. Instrument time goes exponentially. All these factors you have to decide before doing an experiment. So now the question is, how do we choose the dimensionality? We will come back. I'll stop here today. We will come back and tomorrow discuss about how we choose a required dimensionality for a given molecule of your interest.